Binomial theorem deals with expansions of integral powers of algebraic expressions consisting of two terms. For example, a plus b power 2. If we perform actual multiplication, this will be equal to a square plus 2ab plus b square. But there is an interesting pattern that it follows if we take it with reference to the combinations. Here the coefficient of a square is 1. This 1 could be written as 2 combination 0. And power of a is 2 here, which can be written 2 minus 0. There is no b, but if we write b and write power 0, that is almost same as if there was no b. Plus 2ab. Here 2 could be written as 2c1 and then a power 2 minus 1 and b power 1 plus 2c2 a power 2 minus 2, which is of course 0, b power 2. It's just a different way of writing a square plus 2ab plus b square. It doesn't change anything. But if we take a look on this another expansion, a plus b power 3, this actual multiplication will give us a cube plus 3a 2b plus 3a b square plus b cube. Again, if we write the same expression with reference to the pattern we just discussed in step 1, this will also follow the same pattern. Here the coefficient of a cube is 1, which could be written as 3c0, and then a cube could be written as 3 minus 0, which still is a cube. Here there is 1, which could be b power 0 because b power 0 is 1. Plus 3 could be written as 3c1, a 3 minus 1, b 1 plus 3 c2, a 3 minus 2, b 2 plus coefficient of b cube is 1, which is value of 3 c3, a power 3 minus 3 and b power 3. The value doesn't change, but there is a visible pattern if we take it with reference to the combinations. Powers of a are continuously decreasing, powers of b are continuously increasing, and here from first term to the last term, 3c0, 3c1, 3c2, 3c3. It goes all the way. The subscript goes all the way up to n. If we were to follow this pattern, then the expansion of a plus b power n can be generalized. So generalizing this concept, we can write a plus b power n equal to nc0 a power n minus 1 b power 0 plus nc1 a power n minus this was n minus 0 here. This is n minus 1 b power 1 plus nc2 a power n minus 2 b power 2 plus so on, and all the way up to the last term we can write ncn a power n minus n b power n. This is called the binomial theorem. This is what is called binomial expansion or binomial binomial theorem. If we want to prove this theorem, we can prove this theorem with the help of induction method. Let's prove this result with the help of induction. So proof, we use induction method. We use induction to prove this result. So what we do for this is we assume that this statement is true for n is equal to 1. Step 1, that statement is true. Statement is true for n is equal to 1. If this is true for n is equal to 1, then a plus b power 1 must be equal to 1c0 a power 1 minus 0 b power 0 plus 1c 1 a power 1 minus 1 b power 1. That's it. Everything else will become 0, because if the subscript becomes bigger than n, then that becomes 0. So this will become a plus b power 1 is equal to 1c0 is equal to 1, and a power 1 minus 0 is a, b power 0 is 1, plus 1c1 is again equal to 1, a power 0 is 1, but we'll put that value in next term, b power 1. This means a plus b power 1 is equal to a power 1 plus b power 1. That's it. And this is exactly true, which is true. So now for step 2, we assume that statement is also true, that statement is true for n is equal to k. If that is what we assume, then a plus b power k is equal to a power k plus kc. This was kc1. This would be kc0 a and b power 0 k minus 0 here, and kc1 a power k minus 1 b power 1 plus kc2 a k minus 2 b power 2 plus so on, plus kck a k minus k b power k. If we assume that the statement was true, then this should be true. Let's call this as number 1. Now, step 3, we will show that statement is true for n is equal to k plus 1. And for this For this, we multiply a plus b on both sides of equation 1. For this, multiply a plus b on both sides of equation 1. And if we multiply a plus b on both sides of equation 1, this left side will become a plus b power k times a plus b power 1, or just leave it like that. And this kc0, a k minus 0, b power 0, plus kc1, a k minus 1, b 1, plus kc2, a k minus 2, b power 2, plus so on, plus kck, a k minus k times bk. This whole thing must be multiplied with a plus b. That is multiplied with a plus b. And now when we multiply it with a plus b, we will multiply the entire term with a one time, and then we will multiply it with plus b according to the distributive law. So when we multiply the whole thing in bracket with a, every time there will be increase in power of a. So this will become a plus b power k plus 1, because both a plus b, the base is same, the powers will add up. So this will become equal to kc0, a power k will become a k plus 1, because when we multiply a, power will be increased by 1. So b power 0 plus kc1, a k plus 1 minus 1, because we are here again increasing the power of a by 1, b power 1, plus kc2, a k plus 1 minus 2, b power 2, plus so on, plus kck, a power, this will become, since k minus k gets cancelled, so this will simply become a into b power k. This is when we multiplied with a. Now we are going to multiply with b and then add this into this one. So now when we multiply b, this will become akb. So this would be plus kc0, this will be a k and b, plus here kc1, a k minus 1, k minus 1, b power 2, plus so on. And if we continue all the way, we will go to kck, a is 0, so a power 0 times b power k plus 1. Now this time we increased all powers of b by 1. So now whatever we have, since we can see that this kc0, we can write it down here, since kc0 is same as k plus 1 c0, both are equal to 1, therefore we can write it easily, k plus 1 c0 into a k plus 1 and there is no need to write b, but if you want to write, that is b power 0. Plus, now we can take common akb. This is akb and this is also akb. So we can also write this as k plus 1 minus 1. This is essentially same as it is in the first part. Leaving outside, this would be kc0 plus kc1 as coefficient, and here we will have ak plus 1 minus 1 and b power 1. Plus, again same thing, if we take a look on this one, this can be written as kc1 plus kc2, and what we have taken common from both is this is a k plus 1 minus 2 b squared. You can see that this can be written, a k minus 1 could also be written as k plus 1 minus 2. So if we continue like this, and we continue like this, and the last term we get is plus, here this would be the last term, and this becomes, also we know that kck is same as k plus 1 c k plus 1 because both are equal to 1. So this will become k plus 1 c k plus 1 a power 0 into b power k plus 1. If that is the case, now we can replace k plus 1, but instead of doing that in this term, we will do that in next term. So here is what we have is k plus 1 c 0 a k plus 1 b power 0 plus, we use a very important result here, and that result is if kc0 plus kc1, we can add both these combinations equal to k plus 1 c1. In this one and this one, in the upper part we just add 1 and we write the bigger among the subscripts, which is 1 here. So using that result from the combinations, we can write this as k plus 1 c1 a k plus 1 minus 1 time b plus, for the same reason we again have k plus 1 c 2 a k plus 1 minus 2 b 2 plus so on, and then the last term, and that last term is same as k plus 1 c k plus 1 a 0 time b power k plus 1. And now if we replace k plus 1 by n, on the left hand side it's continuously we are writing a plus b power k plus 1. Now replacing k plus 1 equal to n, we get is a plus b power n is equal to a power n, rather this would be n c0, n, we can also write this as n minus 0 b power 0 plus n c1 a n minus 1 b power 1 plus n c2 a n minus 2 b power 2 plus so on plus n c n a 0 b power n, which is again the same statement which proves the binomial theorem. So this is what is called binomial theorem. And in step 1, there is a little correction in step 1. We are not assuming the statement is true. We in fact prove this statement.